So I want to acknowledge upfront that this is work that has been supported by EuFMD, and I'm very happy that I get to present some of it here. So we've already heard about the use of milk testing in terms of disease surveillance, and for FMD, I mean, it's a twofold thing. On one hand, you have the risk that milk can spread the disease, that virus in milk can cause subsequent outbreaks. And on the other hand, you have the possible benefit of milk testing for early detection of outbreaks, as Bryony has mentioned yesterday. So this is different in that respect, that we're not only testing for FMDV here, but also for other diseases that can be shed in milk, that can be carried in milk, such as Rift Valley fever, which also has a zoonotic aspect to it, because raw milk from animals that do have Rift Valley fever can also cause disease in people who consume that milk. Lastly, the third pathogen that we're looking for is BVDV. This is just an old German paper. Doesn't really matter. It's just that the gist of it is the same as we have up here for FMDV, where it says, hey, if you do this, you can have an additional tool in your toolbox in order to detect an outbreak of this disease. So these are the three viruses that we're going for: FMDV, BVDV, and Rift Valley fever virus. And there was a previous PCR, this PCR has been previously used for other samples, so to detect the virus in swabs, serum, that kind of sample. So we took what had already been established for these sample types and modified it to be used in milk. For that, we just had to switch the labels on the probes around a little bit, because in the past it had been used to tell you whether there was FMDV or Rift Valley fever present, but not differentiate between them. So we had to separate the dyes to allow this differentiation. We have Rift Valley fever in the Texas red channel now. We have the very common internal control beta-actin. Then we have one channel for the BVDV and one channel for FMDV. This is just some of the early validation work, in vitro validation work that you do to get these off the ground, where you just look at how do the different targets compete with each other. So we have here always titrations that go at right angles. So you have decreasing FMD V genome here, decreasing Rift Valley over here, and then you just test both of these against a strong constant background of BVDV to see if you have any impact of your CQ values for these other two, which we don't really see here. Same in another combination, strong background of FMDV. You have dilutions of Rift and BVDV, and again, you don't see much of an impact. Where Rift is strongest, you do lose a little bit for BVDV up here, but we didn't think that that was too bad in the grand scheme of things. Last combination, strong background Rift and dilutions of FMDV and BVDV. Same thing again, strong FMDV background increases the BVDV CQ values a little bit. This is a comparison of what you get when you do the individual assays by themselves. So this is on the x-axis compared to the same assay in the multiplex. If the dots are on the diagonal here, the assays perform similarly between these two environments, and you do get that for the higher concentrations, definitely. But then as you go beyond 32, 33, maybe you do lose a little bit of performance in the multiplex assay compared to individual. This is just to show you that the FMDV assay that we were using in this multiplex can detect all 7 serotypes of FMDV, and it can detect a bunch of different subtypes of BVDV as well. We did not have access to any other strains of Rift than the one that we were using, the vaccine strain MP12, unfortunately, but it detects that one pretty well. So in order to get some samples to test this with, we did an animal experiment. We had 3 dairy cows late in lactation, so they didn't give too much milk, so that it was manageable in containment. We did infect them with FMDV type A Iran. This is an A-Asia G7 strain. Infected them by INP, inoculation of the virus. We had a little portable milker in containment, and we milked them once every day. And since we only had 1 milker, we had to be super careful about disinfecting it and cleaning it in between cows in order to keep the sample separate. Well, this is just to show that the infection worked as you would expect. We started seeing the first clinical signs about 3 days after the INP inoculation, just in the mouth here. We did see lesions between the toes as well. Here, some more from in the digital cleft. Here, more tongue. And also, as Phaedra has showed earlier, the typical salivation. And here's some more. And also, there were some teeth lesions. I also have a just H&E of that same lesion. We are going to do antigen detection in these sections as well, but we have not done so yet. And so again, what you'd expect around day 2 or 3, you get an increase in temperature that then goes back down. You do get some increased temperature later on, which I think was due to some of the secondary problems that we did have in these animals, despite us trying to medicate them to avoid that. Didn't really work all that well. So milk yield, similarly, we have a drop around day 3 or 4, where milk yield drops precipitously. We had an earlier drop in this one animal that I do ascribe to just the fact that we had to knock him down for the infection. So here, back to the PCR. We here have the regular 3D PCR in black and the multiplex assay with the same samples from these 3 animals that we infected, and you can see that this is very much paralleled, the detection in the multiplex compared to the 3D, and in general, the CQ values in the multiplex were lower than the CQ values in the 3D. And if you do the same thing, just on a scatter plot, you see it again. So they are very highly correlated with generally lower CQ values in the multiplex, so below the diagonal. This is just a comparison between the different samples that we get from these animals. Milk is in purple, and I'll point that out later as well. But you have fairly standard viremia, then you have a little bit longer shedding in saliva and fluid, but all these are negative by day 12, but milk is not. So virus in milk remains detectable throughout until the end. These are the different milk fractions. There is not a huge difference, but you'll see later on that generally detection in cream was a little bit better, maybe. So first detection, contrary to what I've seen in the literature, we do not really get detection much earlier than the clinical signs appear, so this pretty much coincides around day 3. But it does remain detectable until the end, longer than in serum, and yeah, roughly equal across the milk fractions. So this has been published previously by Pirbright more than 10 years ago. Much higher detection in cream, a little bit worse detection in the skim milk, and a little bit higher maybe in the cells. With us, the differences were not quite that dramatic, but you can also see here that in general, in the cream, the detectable RNA content was a little bit higher than in the whole milk, whereas in skim it was a little bit lower. So essentially the same pattern, if not as pronounced. Then, so this was the in vitro data, then samples from our own animal experiment, and then we got some samples shared from Pirbright, from Nikolaitz and Bryony, from the study that they talked about yesterday, and we tested them in the multiplex as well, and sadly we did not find anything, which I hope in this case really is only due to the fact that what Brioni has shown that their CQ values were beyond the 30s, so they were 30 plus 35, even higher. And I do think that in that range, we are really not that sensitive. If you try to simulate this bulk milk testing with animal experimental samples, so we have milk taken straight from the animals, then we dilute it out. You can still find it if you dilute the milk from a positive cow 1 in 10 in negative milk, but if you dilute it 1 in 100, then in our assay you start losing it, and even with the strongest sample by 10 to the 3 it's gone. So anything that is far beyond a CQ value of 30, I think we just can't detect it here, sadly. So first conclusions here: can easily detect FMDV RNA for a long time. You don't really need to separate the milk beforehand, but I don't think that the sensitivity of our assay right now is sufficient to really be useful for the early detection of an FMDV outbreak in bulk milk, sadly. So I think Brioni's would probably work better for that. As for BVD and RIFT, we still have to do some more real experiments with actual samples to get this done. Do I still have 2 or 3 minutes? Very good, because there is one more thing that I wanted to share that was not in the abstract. This is an outgrowth of what we did in the animal experiment. You have animals with lesions. We ended up with a lot of vesicular material from this trial, and from a different serotype O trial, also lesion material. We had these 2 things, and there's often the question, what do you have to do with, in terms of preservation of FMD material in diagnostic environments in order to be able to detect the virus? And this is strictly for real-time PCR, but with real-time PCR, it doesn't really matter whether you preserve the samples or not. So this is the real-time PCR results at day 0, CQ values of 12 or something, and then we just left these vesicles, pieces of these vesicular epithelium lying around at room temperature. We didn't do anything, no buffer, no preservation of any kind, and the CQ values don't change appreciably at all. So for 3 weeks or longer, while this epithelium was rotting away, you could still very easily detect it in the real-time PCR. We then went and did VP1 amplification for sequencing. Also worked beautifully. We could use here 19-day-old epithelium, 23-day-old epithelium to identify the viruses that were put into these animals originally by sequencing. And if you then use the nice FMDV toolbox from Pirbright, you can drill right down to the A-Iran strain that we have put in the animal in a sample that had been lying around just with no preservatives added for 3 weeks. So that was my second conclusion, just as a little bit at the end. FMD vRNA is so easily detectable in vesicular epithelium that you really don't have to worry about how it's been stored at all. If you're dealing with a real case, real FMDV epithelium and real-time PCR will work no matter what. Thank you very much.